Hi everyone, and welcome back to our lecture video here on section 2.4, where we're using derivatives to find absolute maximum and minimum values. I'm picking up in the guided notes here on page 4 with theorem 9, which gives us the maximum minimum principle 2. So let's start by supposing that f is a function such that the derivative exists for every x value in an interval, and there is exactly one critical value c in that interval for which the derivative is equal to 0. Then f of c is the absolute maximum value over that interval if the second derivative at that location is negative. Or f of c is the absolute minimum value over the interval if the second derivative is positive. Now here's what we have to be careful with. That almost sounds backwards when we read it. But basically what it's telling us is that you can find your critical number just like normal and then actually check it using the second derivative to figure out if it's a max or a min. And that's because the second derivative tells us concavity. So notice here, if the second derivative is negative, that means the function is opening downwards. It's concave down. And notice, if you're concave down, that critical value must be a maximum point on the function. On the other hand, if the second derivative is positive, that indicates the function is opening upwards. It's concave up. At that location, well, that indicates that that c value must be the location of a minimum point. Let's go ahead and put this principle to use by looking at example 2. I'm down here at the bottom of page 4, where they ask us to find the absolute maximum and absolute minimum values of the function f of x equals 4x minus x squared. Now notice in this problem, they don't specify a particular interval. So I'm going to make a quick note here. There's no interval given, which means we must use the entire domain. And that's always the case. If they don't specify a particular interval for you to use, then you must always look at the entire domain interval of that function, which in this case is negative to positive infinity. This is just a polynomial. There's no domain restrictions. Now, this simplifies things quite a bit, because if you have a domain going from negative to positive infinity, we know right away that it cannot possibly happen where a max or a minimum is occurring at the endpoints of your interval. So that's out the window. The absolute extrema here must occur, right? Must occur at a critical value. So we're going to start by finding our first derivative. So f prime of x, and I should say if there are absolute extrema, they must occur at a critical value. So the first derivative is just equal to a 4 minus 2x. We're going to go ahead and set that equal to 0. Let's subtract 4 from both sides. So negative 2x is equal to a negative 4. Divide both sides by negative 2. So x is equal to positive 2. So that's our critical number. Now, and remember, the second principle for maximums and minimums tells us something very straightforward. If there's exactly one critical number over a particular interval, and in this case our interval is negative to positive infinity, we're looking at that entire domain. There's only one critical number. So all we're going to do here is check concavity at x equals 2. And the concavity will tell us if this is the location of a maximum or a minimum. And of course, concavity comes from our second derivative. So over here to the right, f double prime of x, the second derivative. Well, the derivative of 4 is 0. The derivative of negative 2x is negative 2. Notice this second derivative is negative at any location. So if I take the second derivative of my critical number, notice that gives me a negative result. That means our function is concave down at that location. So this indicates a maximum at that location. So we're going to say here that we have an absolute max at the point 2, and then to get the y value, I'm just plugging into the original function. So 4 times 2 is 8, minus 2 squared is 4. So 8 minus 4 is 4. So our absolute maximum is located at the point 2, 4. And the absolute maximum value is 4. Remember, when they talk about the value of the maximum or minimum, it's the y value. So there's a couple of ways you could think about and interpret or express that answer, but they both really mean the same thing. All right. Now that we've seen both of those principles, we kind of want to put everything together into a cohesive strategy. And I've started outlining this at the top of page 5, and it kind of comes in 3 segments. So we've got page 5, top and bottom, and then there's another strategy point on the top of page 6, and then we'll try to put everything together into an example. So, to find absolute maximum and minimum values of a continuous function over an interval, you always can start by finding the first derivative. That's going to be necessary regardless, and that first derivative leads us to our critical values. Remember, those are numbers that make the derivative 0 or undefined. If the interval is closed and there's more than one critical value, use maximum minimum principle 1. And I'm just going to have you add a note here. This would be like example 1. So that's the strategy that we used in example 1. Down at the bottom, they give us an alternative approach. If the interval is closed and there's exactly one critical value, you could use either maximum minimum principle 1 or maximum minimum principle 2. If it's easy to find the second derivative, then I would recommend maximum minimum principle 2. Finally, turning over to the top of page 6, if the interval is not closed, such as negative to positive infinity, or an open interval 0 to infinity, or an open interval a to b, like 0 to 10, but it's open on both ends, and the function has only one critical value, use maximum minimum principle 2. In such a case, if the function has a maximum, it will have no minimum, and if it has a minimum, it will have no maximum. Let's put all of that together. There's a lot being said in those 5 strategy statements. So let's kind of put everything together here at the bottom of page 6 by looking at example 3. They ask us in this problem to find the absolute maximum and minimum values of the function f of x equals 5x plus 35 over x over the interval 0 to infinity. Notice that's an open interval with 2 specific values. Now I know regardless of what principle I'm going to apply, I need to start by finding my first derivative. And to make this function a little bit more derivative friendly, I'm going to rewrite that second term. So f of x is equal to 5x plus 35x to the negative first power, just because I know I'm starting this process by taking the derivative. So over here to the left, I'm going to write that f prime of x, well, the derivative of 5x is 5. And for the derivative of the second term, I'm going to use my power rule. So the negative comes down, negative 35x to the negative second power. Then, of course, you can go ahead and move the exponent back down to the denominator. So this is going to be a 5 minus 35 over x squared. Now, to find critical numbers here, I'd really like to see this as one fraction. So what I'm going to do is multiply this first term by x squared in the top, x squared in the bottom. That way I've got common denominators and I can put these two terms together. So again, just multiply top and bottom by an x squared. So this one fraction is going to be 5x squared minus 35 over x squared. Now, to get critical numbers, you need to think about what makes this derivative 0 and what makes it undefined. Well, what makes it 0? Whatever makes the numerator 0. So 5x squared minus 35 equals 0. Add the 35, so 5x squared equals 35. Divide both sides by 5, so x squared equals 7. And then if I take the square root of both sides, I'm looking at two x values. X could equal positive or negative square root of 7. On the other hand, again, finding critical numbers. So I'm thinking about this. This is my first derivative. What makes it 0? What makes it undefined? We've already figured out what makes it 0. That's positive or negative square root of 7. What makes it undefined is whatever makes the denominator equal to 0, which in this case is just 0. So we've really got three critical values. We don't have, notice we don't have any endpoints to check. So all we have to check on this open interval, and I'm going to list them out in order, is negative square root of 7. Then I've got the 0. And then I've got the positive square root of 7. However, and this is, I alluded to this earlier with example 1, if any of your critical values fall outside of the interval, they need to be cast aside. Those aren't part of this problem. So when you look at this, negative square root of 7, any negative number, that's outside of our interval. Our interval only goes from 0 to infinity, and notice it's open on both ends, so it doesn't even include those endpoints. So negative square root of 7 is not a valid critical number, nor is 0, right? If you look at 0, this is not a closed interval. This interval doesn't include 0, which, by the way, if you look at the original function, 0 cannot be part of that domain, right? 35 over 0 is undefined, so that one is out as well. That means we're down to one critical number, and it's on an open interval. In this case, our best option is to use maximum minimum principle 2. And to do that, we just need to check this x value and see what happens in the second derivative, right? Figure out the concavity. So for this one and only one critical value, we now need to check concavity. All right, so let's go ahead and find our second derivative, f double prime of x. So here's the first derivative written in a derivative-friendly manner. Now take the derivative again. So the derivative of 5 is 0. For the second term, the negative 2 comes down, so that's a positive 70x to the negative third power, or 70 over x cubed. Now notice, if I take this critical value, which is positive, and I plug it into that second derivative, I wanted to write, I wanted to write this as f double prime of the square root of 7. Well, if I plug a positive square root of 7 in here, I'm getting a positive result. That means the function is concave up at that location, which means we're dealing with a minimum value. So we're going to have a minimum at square root of 7 and then we need to find the y value, and then that y value will be the actual minimum. So I know the minimum is at the point square root of 7, whatever y value we get for that, and then the minimum value is that y value. Now, this is not something I'm really going to be able to use the calculator for, because no matter what I do in my settings, I'm never going to see a square root of 7 in my x column. So we'll do this the old-fashioned way. We're going to take square root of 7, and we're going to plug it in to our original function. There's a little bit of arithmetic involved here, so I'm actually going to come up a little bit so we have some room to do this. But we're just looking for f of square root of 7. So I'm just plugging this into the original function. That's going to give me 5 square root of 7 plus 35 over the square root of 7. And now, of course, it's time to simplify. I'm going to start by getting common denominators for these two fractions. For this first fraction, I'm going to multiply by square root of 7 over square root of 7. And then we'll simplify from there. So if you have a square root of 7 times square root of 7, that's just 7 times 5 is 35. So I'll jot that down, plus the 35 from the second term, and that's all over the square root of 7. When you simplify the numerator, you're down to a 70 over the square root of 7. Now we'll rationalize this fraction. You rationalize the fraction by multiplying top and bottom by the square root of 7. So in the numerator, we'll have 70 square root of 7. In the denominator, square root of 7 times square root of 7 is 7. And then we can reduce that fraction. 7 goes into 70 10 times. So 10 square root of 7 is our final y value. That's as reduced as it's going to get. So back down to the bottom here to express our final answer. The minimum is occurring at square root of 7, 10 square root of 7. The minimum actually is 10 square root of 7. Remember, the minimum value is always the y value at that location. So when you look at these two answers, it's really expressing the same information. It just depends on how they're asking the question. All right, that does it for section 2.4, finding absolute maximums and minimums. As always, if you have questions or you need help when you get to the homework, please reach out and let me know. I'm always glad to help.